Hi, welcome to my talk about native applications on Windows. What, why, and hopefully how. So my name is Pavel, and I'm going to discuss this idea of writing native applications, which is not the standard applications we're used to writing on Windows in whatever technology that may be. And I want to show you what native applications are capable of and how to use them on a typical Windows system. So a little bit about myself. I'm a developer, I'm a trainer. I've written a few books and sometimes speak, just like in this case where I'm speaking at least virtually to a virtual audience. And so you can find my books on Amazon and on Linpub. I have a few video courses on Pluralsight and Pentester Academy. I also have a few open source tools that I write. Most of them are targeting Windows and Windows internals concepts, and I have a website with some blogs you might find entertaining. So what are we going to talk about? We're going to see what a native application is and compare that to a standard Windows application that we know and perhaps write on a daily basis. Then I'll give you some motivation of why that might be interesting to write a native application. And we'll see how to run such an application and a little bit about how to write and perhaps even debug such applications. These are not your standard applications, and so you have to do some special things to make this work as though they are standard applications. So if you think about applications on Windows, you might be writing these applications in C or C++, you might be using C# in the .NET platform, maybe Java, maybe Python. It doesn't really matter what language or platform you're using, you're essentially writing a Windows application, which kind of seems a bit obvious. I mean, of course I'm writing a Windows application, but perhaps not that obvious. And so if you go back to history and look at the first Windows NT version, Windows NT actually offered three types of applications you could use and write. One of them is Windows applications. These are the ones that are common today. In fact, that's the only ones that remain today. And then they also offered POSIX, which was specifically POSIX 1003.1, a very basic version of Unix, and also OS2 with version 2.1. And the idea was that Microsoft didn't really know whether Windows NT would succeed. And so they tried to lure developers from other common platforms at the time to take their code and move to Windows. So they said something like, if you have POSIX source code, please bring that to a Windows machine, compile that with a Microsoft compiler, and then the resulting binary will run on the system. And so that application could use the various C APIs such as fopen. It could also use features such as the fork function that is fairly well known in the Unix Linux world, and so on. And that in fact worked on Windows. So that kind of may be a bit surprising to people, is that fork actually is implemented by Windows, although if you have been doing any development with the Windows API, you know that there's no specific function to perform that operation using the known Windows APIs. Also, the ability to have something like two files with the same name, just different case in the same folder, can actually be achieved using POSIX, which means that the NTFS file system driver is case sensitive essentially, and only the Windows APIs that we know perhaps make the NTFS and tell it to be case blind, which means that not all the functionality of the kernel is exposed to the application writer. So the idea was to get developers interested in Windows. However, at the point when Windows NT came finally out in 1993, the other operating system at the time for Microsoft, Windows 3.0, was very successful, and then Microsoft sort of changed gears and focused on the Windows subsystem rather than the other subsystems. So every executable you write normally on Windows runs on top of a subsystem. It links against special subsystem DLLs that are different between these various subsystems. And so if you're writing Windows applications today, then you're linking against DLLs such as kernel 32, GDI 32, and so on. These are specifically the subsystem DLLs for the Windows subsystem. There were other DLLs for POSIX and OS2 at the time. and there's always some process which is the Subsystem Process Manager, which is sort of a helper to the kernel for managing these types of applications. So to see that a bit better, let's look at the quick general architecture of Windows and see how all this fits together. So if you have some user applications, user processes such as Notepad or Paint or Visual Studio or Explorer or Word or whatever else you typically run on your machine. Let's take Notepad as a very simple example. Now, Notepad wants to perform operations such as opening a file. That kind of makes sense. And so to do that, Notepad, being a Windows application, is going to use one of the Windows documented APIs, specifically the function createFile. Now, the function createFile is documented and implemented in one of the subsystem DLLs that you link against when you write such applications. In this case, that's a kernel32.dll API, subsystem DLL. And by the way, don't let the name kernel misguide you. This is still completely in user mode. And so the createFile function is implemented somewhere there. Now, the createFile function can't really open a file. With all due respect, it's still in user mode, and the only entity that can open the file eventually is some file system driver, perhaps, such as NTFS. And so createFile does some parameter checking, all these kinds of things, and then it's going to call another function which is part of Antidll. So Antidll is a system-wide DLL, which is the lowest layer of user mode code. And so createFile is going to call another function which is partially documented, I would say, called anti-createFile. Now, technically, anti-createFile is documented fairly well because it's also available on the kernel side to kernel mode drivers. However, most of the APIs in Antidll are essentially undocumented. And then Antidll with anti-createFile still can't really create any file, but it will perform some operation, which I'll show you a bit later, that makes the thread transition to the kernel into a function called the system service dispatcher, which then calls the appropriate anti-createFile function, the real anti-create function. This is one of the system calls the kernel provides, and then that is implemented by the IO manager, which is part of the executive in kernel space. And that IO manager is going to generate a data structure representing the request. It's called an IO request packet or IRP, and then send that to the appropriate driver, let's say the NTFS file system driver. And then we have a chance of opening the file that Notepad wanted to open at the beginning. Then the function would return with the appropriate result to Notepad, and execution continues from there. So these subsystem DLLs are not the same for every subsystem. So if you had a POSIX application, that would have a different subsystem DLL or DLLs. Same goes for OS2. But the common denominator is Antidll. It's always there because that's the very important DLL that transitions the thread to kernel mode and knows how to invoke the appropriate system call that the client is trying to invoke. So essentially, the subsystem DLLs for other subsystems had to do the same thing, to call Antidll appropriately so that they'll be able to achieve the functionality that they want with system calls that the Windows kernel implements. If you have services are those applications that run like any other Windows application, but they have some interaction with the service control manager. This is the entity that knows how to start services, stop services, pause services, and otherwise configure services. So they're still user mode components just like normal processes, but they have some special powers, such as the ability to run under one of the three special users in Windows known as local system, local service, and network service. And as I said, they have some management aspects provided by the service control manager. However, from an API perspective, they're still Windows subsystem processes, and they use the same subsystem DLLs with the same API to do the things that they need to do. And then there's a bunch of system processes. These are processes we typically don't really think about too much. They're sort of just there doing their thing. And some of these system processes actually don't use any subsystem DLLs. They call directly into Antidll. They actually use Antidll only in many cases without using any of the other subsystem DLLs. And these kinds of applications are native applications. They don't belong to any subsystem. They don't really belong to any subsystem because they can't or won't get a dependency or have a dependency on these other DLLs. So a classic example is a process called SMSS, or the session manager. The session manager is the first user mode process created by the kernel, and that session manager can't really be dependent on anything. The only thing it can depend on is Antidll. We can see that by using tools. So one example is opening any tool that you might have that knows how to look at PEs, at the header and information stored in a portable executable. This is an example of one of my own tools called PL Explorer version 2. So if I go ahead and open something like Notepad, for instance, let's start with Notepad as one very common case. Let me go to System32 and find a Notepad here. So here's Notepad. And we can see here that it belongs to the Windows GUI subsystem, which is really the Windows subsystem. You might find two separate values here. One of them is 2, the other one is 3 for the Windows console UI subsystem, but really it's the same subsystem. It just means whether Antidll is going to create a default console or not immediately. And you can see in the imports that it has lots of dependencies, so it needs to access all these DLLs, and you can see here the functions that it's using from this particular subsystem DLL. So these DLLs are part of that Windows API that is documented. These, by the way, are API sets, which is a way to indirectly map some interface or a set of functions to some implementation DLL, which is something the client doesn't need to know about. So this is not really that interesting for this particular discussion. So if you go ahead and look for something else like SMSS, like I mentioned, we'll see that SMSS has a subsystem of number 1, which is native, which means it has no dependency on any subsystem. It is a native application. You can go to the imports and see that it has a single dependency, which is Antidll only. And we can see all the functions that it's using from Antidll. This is a native application. It doesn't have any dependency on subsystem DLLs. It invokes directly system calls using Antidll and some other functions that are available in that DLL. And so these are system processes, and some of them are exactly as I mentioned, are actually using the native API directly. So lastly, we have something called a Subsystem Process Manager. So every subsystem has a single process manager. For the Windows subsystem, it's csrss.exe, and that exists for every instance exists for every session that is on the system. Now, normally when you run Windows, you have two sessions. One session is session 0, where system processes run and most services execute. And there's session 1, where the first logged in user is logged in. Of course, more sessions could be opened if there are other logins remotely, for example, to the machine. So if we open Task Manager just quickly here, we'll find that we have here two instances of CSRSS, one of them in session 0, the other in session 1, because these two sessions exist right now. And the purpose of CSRSS is to manage in some ways processes that belong to its subsystem. So in the old days, when we had POSIX and OS2, then each one of those had its own subsystem process. So for POSIX it was psxss.exe, and for OS2 it was os2ss.exe. And as I'll discuss in the next slide, these subsystems no longer exist today. And so the focus of this session is really about these native applications, those that don't really need or use the subsystem DLLs and don't care about CSRSS, and they're sort of independent, directly talking to the native API layer that calls the system calls directly, which is part of Antidll, which was used by every subsystem DLL regardless of the actual subsystem. So what happens to subsystems today? OS2 support was dropped in the Windows XP timeframe simply because people just weren't using it enough, so it wasn't worth holding on to that and supporting that on Windows. Even POSIX, which had some use cases at the beginning, eventually was dropped in Windows 8.1. And so today we have sort of the winner is just the Windows subsystem. It's the only subsystem that remains today. So we can only write Windows applications. But there is that extra subsystem, which is the native subsystem. It's not a true subsystem, but as you can see, it has its own value. We can think of that as another subsystem, or if you prefer, no subsystem at all. So that's the native subsystem or no subsystem. And by the way, you might be familiar with a feature that Windows 10 has since version 16.07 called the Windows Subsystem for Linux, or WSL, and you might be thinking, well, maybe it's just the same as one of these subsystems, but no. The term subsystem here is very different from the original subsystems that were created for Windows NT usage, because the original subsystems required the source code to the application. The application had to be recompiled with a Microsoft compiler, and then a PE was created, and that would run on Windows. However, WSL is much greater, and in fact is much more ambitious. It says, please take a Linux executable, already an existing executable, built with the ELF format that is used on Linux. You don't need any source code, don't need any compilation, just drop it on Windows, run it, and that will work. And that of course requires some very different support to make that actually happen. And the basic idea for WSL version 1, which is the currently existing version, and version 2 actually just came out in the latest version of Windows 10, at least at the time of this recording. And WSL 1 works on the basis of something called a Pico provider, where we have a driver written by Microsoft that knows how to translate Linux system calls to the appropriate Windows system calls so that this could actually work. So what we are installing with WSL is actually the user mode part of Linux, and the Windows kernel simulates, if you will, the Windows kernel simulates the Linux kernel, if you will. And so we only have the user mode part in WSL 1. So WSL is not part of this discussion. Just know that it is not implemented in the same way as the classic subsystems were at the time. And so native applications are those applications that don't use any subsystem, don't have any such dependency. They can only link against Antidll and use the API provided by Antidll. So what can you find inside that Antidll anyway? So what can I use if I'm writing just a native application and only have a single DLL I can use? Then I really hope it has enough functionality for me to do stuff. Otherwise, I'm kind of a pickle there. So first, Antidll implements some very important components which need to be used in user mode, such as the image loader, the ability to load other DLLs, for instance, and some other functionality that is required, especially when the process starts up. It also implements the heap manager. The heap manager is there to control small allocations, because the normal APIs for allocating memory that are very close to the memory manager only work in large chunks, that is chunks in size of pages, and every page is 4 kilobytes by default. So if you want to allocate 10 bytes using that API is going to be very inefficient, because you're going to get a page anyway, even though you just need 10 bytes. If you ask for 10 more bytes, you'll get a different page. So the heap manager is there to provide a higher level abstraction where it knows how to manage these smaller allocations. Some support from the thread pool is also part of Antidll. The other functions you might find in Antidll are those that you might be familiar with from the C runtime, such as memset, sprintf, and all these kinds of fairly well-known functions. So they're there exactly to help native application developers have an easier time. So if you want to implement something like sprintf and you can't link against the Microsoft Visual C runtime because this requires subsystem DLLs from the Windows subsystem which you cannot use, then how would you implement that? So you're very happy probably that you have this support as part of Antidll. And so if you go to the PE Explorer here or some other exploration tool, in that way we can open Antidll and see its exports. So you can see the various functions that are available in Antidll. These are all the functions that can be used from native applications, of course. So this is everything there is. And if you scroll around, you'll see that functions such as sprintf and even sqrt and even assign for an angle is there. You have a qsort. So all these kinds of functions that are fairly well known from the C runtime are actually implemented in Antidll as well. So it's not the same implementation you might find in Microsoft Visual C runtime, because this implementation is different and it has no other dependencies. So it's nice that Microsoft thought it's a good idea to put these things there, because it makes writing native applications a bit easier once you have all these nice C-style function support. The other stuff that is Antidll, which is probably the most important one, is these system call invokers. So this is where we have the code that knows how to jump into the kernel and invoke a certain system call or system service, such as the anti-create file that I mentioned earlier that Notepad will probably need to use. In fact, it will use that. And we can see that using a debugger, but we're not going to do that in this session. Just to show you what that code looks like, so here's the dispatching code for 32-bit and 64-bit. The essentials are the same, the implementation a little bit different. So the idea here is that if I want to invoke a certain system call, I have to set a value inside the EAX register, and I'm talking here about Intel AMD processors for ARM or ARM64. This is fairly the same idea, just different register and of course different instructions, but the concept is the same. So for this particular 32-bit operating system where I took this snapshot, the value 8A hex represents the anti-read file system call. And then we have the sysenter instruction, which makes the transition, the quantum leap into the kernel, into that system service dispatcher function, which is prepared up front using that sysenter instruction. So this is just calling a function that was programmed initially when the kernel was booted, and that function takes that EAX register and uses that as an index into a table of function pointers, just calls the appropriate function, which by the way has the same name and the same parameters as the one in user mode. So we have another function called anti-read file on the kernel side that does the right thing, so does the actual implementation, which for the anti-read file, in the anti-read file case, it's part of the IO manager. For 64 bits, it's exactly the same idea. And so in this case, anti-read file, the system service number is actually 6, and then the instruction is a different one, it's called syscall, but the effect is the same, and the way the table of function pointers that is stored in 64-bit is it's different actually than 32-bit, but conceptually, logically, it's exactly the same thing. Just use EAX as an index into some lookup table and then call the appropriate function to do the right thing. So this is how system calls are dispatched in Windows. And so this code is part of Antidll, which knows how to put the correct number for each system call so that the dispatching is correct, of course. So why would you want to write native applications? So one reason is that you can run some of these applications at Windows Startup. The most famous application is AutoCheck. So if you sometimes have your Windows shut down unexpectedly for whatever reason, then you get, once you restart the system, you get this prompt saying, what about, let me just check your disk or something. So this is done by an application called AutoCheck, which is native. It can only run, it runs very early in the Windows boot sequence, where only SMSS is at this time available. The Windows subsystem is not yet up, so CSRSS is not yet up, because, by the way, SMSS is the one that's creating it later on, and so you can't really link against anything or depend on anything except Antidll. And so AutoCheck is a native application. If you go ahead and open AutoCheck just to verify that, so here's AutoCheck. You can see it belongs to the native subsystem, and again, its only dependency is Antidll. And by the way, there is another application which performs essentially the same operation called CheckDisk. And CheckDisk is a Windows application, so it depends on the Windows subsystem being available, so it can only run later on once a user is logging in and so on. But AutoCheck can run very early, and you can run your own applications that run this early. The way to do that is to add your application to this particular key, and there's a value there called boot execute, which is a multiple string value, and you can add your application there. The only thing you have to make sure that your application is in the system32 directory. So let's see, maybe you can do that as well. So here I have a very simple application called just simple. This is just a good name, I would guess. And so we have this simple application. I'll discuss the code later on, but for now let's just see if we can copy that to a virtual machine and see when that and copy that to where it's going to execute once the system boots up. Let's go to a native debug here, which doesn't really matter. So actually I think I put that under debug. So let's do that. Make sure we have the correct version. So here's a simple. Let me just take the executable. Here's a Windows 10 virtual machine lying around. So I'm going to copy that to temp here, but to make that actually work, I have to go to system32. That's the only location that is viable for running these applications when the system boots up. So here's simple.exe. So now let's go to the registry and see what's going on in there. So I've already opened here the key that I mentioned in the slide. So that's the session manager, and here's the boot execute value here. So you can see that by default it has this AutoCheck, AutoCHK, and star. And so AutoCheck, the first text is just some user defined text. It has no meaning if the executable is specified here, and so this is just some string. Then you have the executable and any command line parameters that it needs. So I'm going to just add simple here so that both of these can execute next time the system restarts. So I'm going to now restart the system. So what my simple application does is just write sort of a hello world kind of text on the window that we typically see when Windows restarts. So let's give it a few seconds for my system to restart. You can see here the hello native world text. That's my application doing something, which is, I guess, not very exciting, but still shows the fact that the application was running in the very early stage of Windows execution. So now let's see what that code looks like. How is an application written to be native? So here's my very simple hello world style application. And so the way this works is that I have to use the native API. Now, unfortunately, most of the native API is undocumented. Some of it is documented a little bit because some of these functions are documented in the Windows driver kit for use by kernel device drivers. However, most of the functions are undocumented. In any case, there have been lots of reverse engineering for these functions, so at least we know their prototypes, and some of them actually make sense and fairly intuitive to use. But still, there's no official documentation for most of these functions. So let's see the basics of just a very simple hello world style application. So as you can see here, there's no main function here. So the main function that we typically write for C or C++ application cannot be used for these kinds of applications, because the main that we typically write is actually being called by the C runtime startup code, which we link against in any standard Windows application. But here we don't have any Windows startup code. There's no C runtime here, and so the main function is actually different. It's called anti-process startup, and it accepts the process environment block, which is a fairly well-known user mode data structure that contains all the information needed for the application to start up. .pb is created by Antidll when the process starts up, and so it contains, for example, the full command line of the application. So if you need to access the command line, it's somewhere in there. And another thing that we should understand here is that the process is not going to be terminated automatically. We actually have to terminate that explicitly using the anti-terminate process function. So first, as far as includes are concerned, I can use include windows.h to get the basic types that Windows supports, which are also used by native applications, but of course most of the functions defined there, which are part of the Windows API, I can't really use. So there's another header called winternal.h that provides some definitions that is part of the native API. Very few of them, and some of them are actually missing some information, but still that's better than nothing, and it's something to start with. So for example, this function RTL init Unicode string is defined in winternal.h, which doesn't require me to provide the definition myself. However, every other function that I really need to use, I'll have to define that here by finding somewhere information about the prototype of these functions, just copy them here or use an existing header file so I can use these functions. So in this case, I've used three functions here. One of them is anti-drawText. This is the function that allows me to draw the text that we've seen when the system booted up. That was here the hello native world that I've initialized this Unicode string structure, which is a very common structure to use for holding strings, UTF-16, Unicode strings, within Antidll and within the kernel itself, by the way, because Antidll is tied to the kernel in very strong ties, I would say. So this is the anti-drawText call that actually accepts a Unicode string, and I've initialized that, and that's why we saw the text that we did. Then we have this function anti-delay execution. This is in fact the native API that is used when you call the Windows API sleep, which is a very simple and kind of famous API, but there is no sleep directly. This is the sleep, and so I wanted that text to remain for a few seconds so you don't miss it. So I wanted to sleep to let the current thread wait for 5 seconds. So the way to do that is to call anti-delay execution. You can see that first parameter is whether the thread is going to be in alertable state while sleeping. And I'm not going to discuss alertable state here, but essentially the sleepEX function from the Windows API allows you to be in alertable state at that time. In any case, the most important parameter is the second one, which is the interval to wait, to sleep. And so the normal sleep function we typically use in a Windows application just accepts the number of milliseconds and that's it. The native API anti-delay execution is a bit more complex. It requires the time in a certain format, and that's in units of 100 nanoseconds. So that's a very common unit in the kernel in Antidll. It is less common in the documented Windows API. In fact, negative numbers mean that I want something relative, so 5 seconds from now. So this is the sort of the transition or the translation between this 100 nanosecond unit to the 5 seconds that I want. So this is the delay I get here. And finally, I need to use the anti-terminate process to terminate my own process. So I need to have that declaration available here as well. And because I'm using C++ here, I have to use extern C to make sure that these functions are imported as C style. Otherwise, that will not work. And so what I have here is a basic application, but that's really not enough. How do I build that to have no dependency on anything other than Antidll? And so Visual Studio doesn't provide a template to write a native application. So we have to actually do some work to make that actually compile properly and compile without any of these extra dependencies. So the most important thing is going to the linker tab in the system option here, specify native. This is not the default. The default is the Windows subsystems. You can see there are several options here, and the default is Windows or console, depending if you're creating an application with a GUI immediately or just a console application. I'm going to change that, or I change that to native, but that of course is not nearly enough. We have to remove all the other dependencies. So for instance, under input, I'm going to remove all the dependencies that are typically stored here and just say that I want to depend on antidll.lib, which is the import library for using antidll. And I'm going to say ignore all the default libraries. So all the other standard libraries from C or C++ or whatever, I don't need them, I don't want to depend on them, and I can't. If I do depend on them, then that application will not be a native application really, and it actually won't compile properly, and definitely not run once I set that up in a boot execute value. So that's another thing I have to do. For C++ tab here, there's some other stuff I need to do. I need to remove most of the checks that are being performed and some features that are specific to C++ that just cannot be supported because there is no C++ runtime when you're working with a native API. So for example, I've removed the ability to use C++ exceptions, and I've removed all these security checks which are provided by the C runtime. We have these certain security checks to make sure there's no fishy thing going on with stack manipulation, so I can't really have that anyway. The basic runtime checks, typically you have these both these stack frames checks and making sure you don't access uninitialized variables, but still that is part of runtime checks which are provided by the C runtime, and we don't have a C runtime to work with. So essentially I'm kind of trying to turn off everything that I possibly can until I get proper compilation and linking with that particular code. So this is the idea of how to create a native application. So let's go back to the slide. So we've seen the boot execute, and so to launch them, when we put that in the boot execute value, that's easy enough because SMSS is the one responsible for launching all these native applications that are part of that boot execute value. However, what if I want to launch a native application just like that, just like I'm double-clicking a normal application in Explorer and hope that application would run? So behind the covers, Explorer is calling a very famous, well-known Windows API function called createProcess. Unfortunately, createProcess is unable to launch native applications. It can only launch Windows applications. And so we have to create our own sort of launcher that knows how to launch native applications. And so the way to do that is to write some code which is going to be a normal application, normal Windows application. I've created one of those. It's called the native run. It accepts a parameter in the command line which is the path to the executable you want to run, and then it just runs that as a native application. And of course, if it has other dependencies, then it can run that as well, but it is specially used for native applications. And so I can't use createProcess. The way to do that, to actually run these things, is by using RTL createProcess parameters. This is another Antidll function, by the way, which is undocumented, but still something that we have to use here, because we have to kind of perform the creation of the process in steps that are normally taken by createProcess, but createProcess sort of avoids or rejects applications which are native. So we are going to do some of these steps ourselves so that this creation is not rejected. So I'm going to call this function to create something called process parameters. And once I get these process parameters, I can call the RTL create user process, which is another helper provided by Antidll, where we need to provide the name of the application, so the path to the application, and here's the parameters that we created previously. And if all goes well, we get the proper process and a thread ready to go. The only other thing that is left to do is to resume the thread, because the thread that's created here is created in a suspended state by default, so we have to kind of push it to start execution. That's going to be done using the resume thread function. So that's the idea. Let's see if we can make that, how exactly I'm using that to run something. And so I'm going to open a command line here. And so let's go to native debug. and x64, maybe x64 first, and then native debug. And I have an application here. If we look at that, there's an application here called list privs, which is about listing the privileges of the current process. So if I run that under boot execute, for instance, I'll see all the privileges that I have running at that particular point in time. And by the way, we're going to have every possible privilege by almost every possible privilege by running at that early point in time, which is very nice because it means we can do actually anything. And so if I try to run that directly, then you can see that the command line interpreter can't really do that. It's also calling create process behind the covers, and we get an error. It says it can't be run in Win32 mode, which in fact is correct because this is not a Windows application, it's a native application. So I'm going to use native run to run that. So let's try that out. And now we get some strange error, and that error is C0003B. This is an anti-status which is used in Antidll and the kernel, and so we can try to find out what that means by perhaps Googling, but we can do some other thing. Maybe I'll just open WinDebug. I'm not going to discuss WinDebug here in detail, but if I just attach to the kernel or my local kernel or just debug anything, we can use the error command to get some information about that error. And it says object path component was not a directory object, which essentially means that something is bad with this particular path. It's not really a good path. And so maybe the command really needs is a full path to the application. So great, let's go with c dev temp and native apps and x64 and then native debug, and then our application is list privileges like that, and we'll try that. And apparently we're getting the same error, and the reason for that is that in the native world that C column doesn't really mean a whole lot. The path actually has to be in something called the anti-device form path, which is not starting with C column. In fact, we can see that in WinObj, in a tool from sysinternals called WinObj. This is one way of viewing that. And if we go to this directory called global 2 question marks and look for C colon, we'll see that C colon is in fact a symbolic link to something called device hard disk volume 3 on my machine. So perhaps if I try to use device hard disk volume 3, then I'll be able to get to that particular disk. So let's try that out. So hard disk volume 3 and then the path to the actual file. And if you do that, it actually succeeds. The application now runs correctly. Process with this particular process ID has been created, and the process is already gone because it's only the process actually opens the file and writes all the privileges into that file, and it writes that to ctemp just as an example. So here's the file. Notice that is exactly 1 minute ago, so it's 18:05. Notice my clock is 18:06, so in fact this is exactly the same the file that's created right now. And if we open that, just by looking at it, we can see the 5 privileges that I currently have. One of them is enabled. So this is the privileges that my access token had when that process was running. And so we can see the privileges as just numbers. We need to convert that to their string representation for clarity, but these are the privileges, and this actually happened just now. And so I was using this device path because this is what Antidll understands. C colon is just too high level. However, it is possible to use C colon if we wanted to by invoking this same idea of symbolic links. Because if you go through these 2 question marks directory, this is a logical directory in the object manager's namespace, it's not a real directory, then we can use C colon as well. So let's give it a shot. Let's just go ahead and prepend that with 2 question marks, and so that actually says let's go to symbolic links directory and then start from there, and then C colon should be translated automatically by the symbolic link mechanism to the appropriate hard disk volume 3 as we've seen earlier. and as we try that, it succeeds again. And again, we can verify that by seeing that the file is a new one. Let's refresh here. It's 1807, which is exactly now, was created just now by running this particular process. So this native run application allows you to run any native application right here without having to go to boot execute, and that makes it easy to first test this on perhaps just a standard native application here when the system is normally up, and only then, if you do intend this application to run with boot execute, then try it with the boot execute option. And so let's try that out with boot execute. Let me take these privileges here and go back to my virtual machine. Let me first put it here in temp, because we can't with Hyper-V copy it to a admin related directory directly. So I'm going to copy that from here to system32. So it's here. Let's refresh just to make sure. Okay, so we have these list privileges. Here it is. And now I can go back to my registry. I can remove, simple or not, doesn't really matter. But to make it a bit faster, let me remove that and just leave list privs. I believe that's the correct name. Yep. And then again, restart the system and see what we get. So currently, notice the ctemp folder doesn't contain any text file, and that text file is going to be available if everything goes well once the system restarts and my list privileges is going to run. Okay, you can see perhaps briefly it was privileges 31. I also used anti-display text again, or draw text, to display the number of privileges. But we can make sure now with the actual list of privileges that we'll find in the file if everything actually goes well, because the draw text doesn't really promise that everything is fine. So let's see, and indeed we have this privs.txt file. If we run that, open that in Notepad, we can see all the privileges that the process had inside its token. So you can see the 31 privileges here, and almost all the numbers are here, including super powerful privileges such as the TCB privilege and the create token privilege, which essentially means you can do anything. You can impersonate any user, access any system resource at that point in time. So you actually are given lots of power, and you can just use that to do almost anything. I'll let your imagination think about what you can do at that point in time while there's nothing running on the system except SMSS and your process. So at this time you can make preparations before other processes are going to launch later on, because the Windows subsystem is just not there yet at that point in time. So you might be wondering what's the code in list privileges. So let's see what that looks like. And so again, I have to add some functions that I need to use, such as anti-terminate process, delay execution, draw text, and here are some new functions. In this case, I'm going to use anti-query information token to get information from the token, because the token is the one that stores the list of all the privileges that are available inside that token, and that token is attached to my process. And then I need to open a file to write some information to the file. I'm going to use the anti-create file function for that, the same one I mentioned earlier. In this case, WinTernal already defined that function, so I'm good. I don't have to do anything about that. However, I do want to write to the file, so the appropriate function is anti-write file, and to close handles I have to use the anti-close function. And so if we take a look at this function, the helper that I'm calling from my main function, and we can see here I'm going to call anti-query information token to get the token from my process and get the information about the privileges that are going to be stored in some buffer. And then I'm going to just go ahead and iterate over these privileges and write them to a file. Now, if you're familiar with the Windows API, this function is very similar to the get token information function that is documented. And in fact, it uses essentially the same parameters, so it's fairly easy to use if you know about get token information. So it looks a bit different, but essentially it's the same data structures, the same enumeration here to get that data. So what I'm doing here is using swprintf here, which I am happy is part of Antidll, to format these privileges with the number of privileges that I found, and then I'm just using here anti-draw text to show that text. And the idea here is that I'm using an if-def here for this constant called native, so that I'll be able to more easily test my application even from a non-native application essentially, but still calling native functions. And I'll discuss that in a moment when we look at debugging. So once I have this data structure in place, I want to open the file. So to open the file, I have to use the anti-create_file function, which is non-trivial. It has many parameters, but they're not that complex, but it is more complex than the standard create file function you might be familiar with from the Windows API, the documented one. But essentially, we have this object attribute structure here, which is very common in many APIs, and the file name is actually in there. So I have to initialize these object attributes, and the file name is just there, and it's being initialized with a particular name, which is provided by this path parameter here. So once I have that in place, I'm going to call anti-create_file. The result, if successful, is going to be placed into this handle here, the hfile variable here. And if it works well, then all I have to do now is to perform some write operations using the anti-write_file function. And so I have this first text, which is the number of privileges. I'm writing that to the file, and then I'm looping here on all the privileges that I have, getting each one of these privileges and writing some text to that regard, using again sprintfs for easy formatting and anti-write file to make the actual writing into the file. And then I'm calling anti-close file, and I'm done. So this function is called here by calling this here from the anti-process startup function. As we know, it's the standard function for entry for all native applications. And notice here I'm using that same syntax, otherwise this just won't work. Anti-create_file is a very low-level function. It expects things in anti-device form, which means using device hard disk volume 3, but because I don't know exactly what the device name is going to be on whatever machine that's going to run, it's definitely easier to work with the symbolic link here, because C column is likely to exist on any machine. Of course, in a more practical example, I'll probably do some enumeration and to make sure that C doesn't really exist. But let's, for this purposes of this demonstration, let's assume that easy. And then I'm going to just call this function, and this is just a small delay just for demonstration purposes, and then I'm going to terminate the process. So this is the way this particular code works. And there are some other nuances here which are not that important, but you can look at that later on when the source code is available as part of this session. So let's go back to the slide. So we know how to launch native applications normally, and the only thing remaining is just to discuss some other odds and ends related to native applications. One of them is about writing. This is just summarizing the things that I already mentioned. So we have to use native API from Antidll. There's really nothing else we can do. Mostly it's undocumented, and that's one of the challenges for writing native applications, because some things that you want to do, you might not know how exactly to do that. So you have to do some research, and one good location to find all the functions is the Process Hacker project on GitHub. So some functions are partially documented. Some of them are fully documented indirectly in the Windows driver kit, because we know that system calls are also available in the kernel, because these are exactly the same functions, where in Antidll is just sort of a jumper to the kernel, and then we have the actual implementation on the other side. And so functions such as anti-create_file, in fact, are fully documented. So let me show you that. So here's my offline documentation, but you can, of course, use the online as well. If you go to anti-create_file, you see the definition, and you can see the full documentation for anti-create file. So for anti-create file, life is relatively good because we have full documentation. Same goes for anti-write file, anti-read file, anti-close, because drivers need to use them also. And many other functions, by the way. But of course, not everything. So some functions you have to sort of guess or find information online. And as I mentioned, we need the prototypes of these functions. So those that are documented, we have the prototypes, but those that are not, we don't. And one very good location to get all that is in the Process Hacker PHNT project that lists practically all, or at least most, of the function prototypes with all the various enumerations, whatever else you might be needing, so you can really have lots of stuff to work with when you're writing those native applications. So we've seen list privileges. That was the other application I wanted to show. And last thing I want to just discuss here, I'm not going to demonstrate that, but it's something that you should try it out. How do you debug native applications? So as we've seen, you can't really attach or debug that directly using Visual Studio or WinDebug because they rely on the same create process function to launch the process and attach to it. And we know that create process just can't be used to launch native applications. So what do? So one option is to build your application in a way that you're using native APIs, but you can also launch the application without that being a truly native application. And so, for example, if you go back to my list privileges, notice I have this native macro here that I've defined for the native type, and I have a normal main function here that just invokes this functionality. So I can compile this application in really two ways. That's why I have these extra configurations. So one of them is the native configuration, which removes all the dependencies and makes sure the subsystem is native and so on, as we've seen with the simple case. But there's also a normal debug where we are going to use that as just a normal application. That makes it easy to debug because I'm using the same native APIs, which I can, but I can attach to Visual Studio and debug sort of normally. So that makes it fairly easy to debug. However, not all scenarios can be debugged like that. So for example, in the case of boot execute, I really can't debug it in this way, and the conditions may be different. So in the case of privileges, for instance, then we've seen that the privileges running locally after the user is logged in with some standard user rights, we have only these 5 privileges there, but when running under boot execute, we have many more privileges, so we can't really debug the real scenario in that case. And so it's still worth doing that because it is useful for many cases, but if you do want to debug something like boot execute, then apparently it's just not good enough. The other way you can debug that, which you can debug that fully, is by using a kernel debugger. So if you attach a kernel debugger to the machine you're trying to debug, in this case, for example, my virtual machine, I can very easily, just like any other kernel debugging scenario, I can break in any location that I want, including a particular process with a particular executable, such as my own list privileges executable or some other executable I'm trying to debug. So I can debug that indirectly using kernel debugging, and I can also do that while the boot execute is being read by SMSS, and it's the one launching my application. So it is possible to do. We don't really have time to demonstrate that in this session. However, if you know something about WinDebug and know how to use the kernel debugger, then you should be able to do that without any special issues. If you're not familiar with WinDebug, then naturally that doesn't make sense a lot to you, but I do urge you to look at 2 of my courses on Pentester Academy that introduces anyone that's interested to WinDebug in user mode and WinDebug in kernel mode. So once you do that, you'll be able to debug these native applications as well using a kernel debugger. And so this is what we have here in this session. I've shown you how to write simple native applications. Naturally, there's lots of stuff that is behind that, but just to get you started here. native applications have no dependencies. They only depend on Antidll. They're stealthy in a way because CSRSS doesn't know they exist. I'm not talking about those running under boot execute because these are definitely not known by anyone because they're running very early. But even if you run native application later on, once the system is already up, still these processes are relatively more difficult to locate if you are concerned about these things or trying to build something which is more stealthy and much harder to detect. And many anti-malware solutions, for instance, just ignore native processes because in most cases native processes are provided by Microsoft and are also protected, and so they're not very interesting from a security perspective because it would be very, very difficult to gain some access to one of these processes. So if you are providing your own native application, your own native process, then you might be ignored by anti-malware software. And we've seen that this is the only way to run these applications in those early times when SMSS is the only process around. And we've seen also that it has all possible privileges essentially, and you can do practically anything at that point. So you can prepare even for executing some other application, perhaps later on, you can prepare at that point something that could be useful to another application running later on, even though that application may be just a standard Windows application. So thank you for being with me in this session. I hope you enjoyed it. And the source code will be available as well as the PDF slides. So thank you and have a great day.